All right, next set of Hydrosphere Notes, we're going to start here at Groundwater Notes. So this page, if you can totally see it or not, whatever, doesn't matter. Groundwater Notes, that's where we're at. We're going to start at Confined and Unconfined Aquifers. So in the name, obviously that helps you kind of understand what's going on. Confined means that it has a rock layer on both sides of it, something that's keeping the water from being able to interact with a lot of the ground surface. Now, there's some interaction because otherwise, you couldn't get to it and you couldn't recharge it. But it doesn't really have interaction with the surface, and it doesn't have any contact with the water table. Unconfined, that's obviously, not confined by rock layers, and it has interaction with the water table. It's a lot easier to recharge. It's a lot easier to get water out of it. It's going to be used a lot more. Now, why does that matter? Well, we need to understand how groundwater and surface water work so that we can kind of figure out where we get our water that we use. Now, we know that most of the Earth is covered in oceans, but we can use desalination processes, but it's kind of expensive and it's kind of time consuming and energy consuming, so we don't really want to do that. We're going to use groundwater and surface water. What we see sometimes, though, is specialized circumstances where we have caves and disappearing streams and sinkholes and stuff like that. It's going to be associated with what we call karst topography. And a lot of it's going to have to do with limestone formation and the erosion of limestone. And it forms, you know what a cave is, you know what a cavern is, you've seen all that. We typically see it in areas where we have to be careful what's under the ground, because like we talked about with the Taco Bell in Wilkesboro, if you build on that and there's nothing under the ground, eventually it's going to collapse, it's going to have a sinkhole, it's going to form a cave, something like that. We also need to understand that the water can sometimes be heated and pressurized, and we get springs and hot springs and geysers. And when you put enough heat and enough pressure, you get a geyser that erupts, like Old Faithful. And basically what happens is the water goes to the surface, and you know what happens if you heated something up on the stove and put the lid on it. Eventually, it's either going to explode or it's going to completely evaporate away. Well, since water is still recharging the hot springs and the geyser, it's not going to just evaporate away, but it is going to erupt. We can also look at groundwater depletion, and that's when water leaves the ground and you get subsidence. So remember how we talked about in lithosphere that magma chambers, when they start to erupt and they disappear, we can see the ground kind of sink, and we call that subsidence. Well, the same thing is happening here, but rather than magma, it's water under the ground. So if it's an open chamber, a cave, if you want to think of it like that, and the water leaves it, the ground's going to sink. If it's heavy enough, the ground's going to collapse. All of this, groundwater and ocean water and surface water, we can then tie into streams and how streams work, and the discharge of streams and the velocity of streams. We know that younger streams are going to be faster, they're going to be more narrow, you're going to have rapids in them, they might be more fun to go, take a raft or a kayak or something in. But older ones are slower and wider and flatter. They've had more time to carve out the landscape, to change the topography. Think the Colorado River. It made the Grand Canyon. It is incredibly old, and you can see that it's not that fast moving now. But if you look at the rock layers, you can see that it has been around for a really, really long time. We also know that if you take a random point, it doesn't matter what point, but if you take a random point of the river and you calculate how fast the water is moving there, and you calculate the area of the river, you can figure out the discharge. So it's the area, length times width, or depth times width in this case, multiplied by how quickly the stream is moving. That's going to give you stream discharge. But also what we use to figure out, or not necessarily figure out, but use to analyze, is what size particles can this river or stream or whatever it is you want to call it move. That's what the chart on your reference table on page 6 or 7 is for. You use that black line and it's got the 6 different sediment sizes on there, and if you want to know the velocity, look at the x-axis, and if you want to know the sizes, look at the y-axis. Wherever those lines meet and wherever the intersection of that dark line that's already made there for you, that's going to give you your information. Now, if you don't understand that, please ask me. You might have to do that. You might not. Better to know it just in case. We also then need to understand that weathering and erosion are not the same thing. Water is the biggest transportation of erosion. Erosion is actually the movement of that broken down material. Weathering is the breaking down. You have chemical and mechanical weathering. And mechanical weathering is when you break stuff down, but it stays the same thing. So if you mechanically weather a granite, then it's going to stay granite, it's just going to be in smaller pieces. If you chemically weather it away, it's going to change its chemical composition. Colder, drier climates are going to be better at mechanically weathering something. Hotter and wetter climates are going to be better at chemically weathering something. So the Arctic is going to be good at mechanical weathering. The equator and the tropics are going to be good at chemically weathering something. All of this is to say that when any of this happens, it eventually is probably going to end up in a river system. And when it gets into the river system, it's in a watershed. A watershed is just anything that is carried away or is drained or it eventually makes it to that river system. So where we're at, we're in the Yadkin PD watershed, which means eventually the water is going to make it into the Yadkin and eventually the PD River. That is going to go to the Atlantic Ocean. But if you go somewhere else in the state, you might be in the Dan watershed, or you might be in the Neuse River watershed. You might be in a different watershed. It's all still making it in the eastern half of the state to the Atlantic Ocean. But once you cross the Eastern Continental Divide, like you're on the way to the mountains, you're eventually going to have to cross over the highest point of the mountain in that area. It's going to go to a western source. Well, all those rivers eventually are going to dump out into the Mississippi. And the Mississippi is going to take it to the Gulf of Mexico. The divide is simply the highest geographical point between watersheds. So the Eastern Continental Divide are the Appalachian Mountains for us. But the watersheds are any area that's drained that goes into the same river. Hopefully that helps make a little bit more sense. What else do we really need to understand with all of this though? That water, when it goes to the oceans and when it gets dumped into the Gulf of Mexico or wherever it might be, it's going to eventually meet with the larger body of water. That area is called a delta. When a stream or river empties into a larger body of water, that's called a delta. And these can sometimes be special if the freshwater river is emptying into a saltwater body. It can form a specific ecosystem called an estuary. And this is, crucial because only certain organisms can live in these estuaries. Some of them go to hunt in estuaries. Some of them go to reproduce in estuaries. And we look at satellite images like the ones that are in your PowerPoint, and we can see all the sediment that is taken from the river and dumped into the Gulf of Mexico, which is the example that you have. This also gives us a lot of information about how much actually makes it through the river. Where do they end up if they don't end up in the water? Well, it ends up on the beach. So why in the mountains do we have a bunch of different types of rock, but at the coast we only have sand? Well, eventually it all kind of just gets filtered through, and the only thing that makes it all the way from the western part of our state to the eastern part of our state is the sand. Now, silts and clays too, because they're little tiny particles, but not big boulders and cobbles and stuff like that. That's not going to make it all the way down. And if it does, it's going to eventually get weathered, and that weathering is going to erode into smaller particles like sands and silts and clay. That kind of is a very quick rundown of those things. We're going to talk about the oceans in the next video. Hopefully that helps a bit. I don't know. Most of you don't watch this, so I don't really know if it's a point of making these videos or not. But if you do watch it, hopefully it helps. Thanks.